Hello everybody, welcome again to our course ETABS and SAFE and 11 meter span slab. Now we will go to import our model, ETABS model to SAFE. And the SAFE is the most important part of our course. It is the design and analysis of our slab. We will show an ETABS that we define the material, define the loads, define the sections of element. We put the slab 30 centimeter, the material of the slab 25 F prime C equal 25 megapascal, and with the columns with 30 megapascal. Okay, and we do the modeling of the slab and to put dead load 5.5 kilonewton per meter square and live load for residential building equal to 2 kilometer per meter square. Okay, and now and we export the model to SAFE. Now we will import this model to SAFE and do the analysis of our model. If we go to SAFE, this is the home page. We go to File, Import, SAFE. The extension of the SAFE is F2K. Okay, File. So we go to here. We go to desktop here. Okay, save. This is the file that we export. Press open. We can show now here is our model. Okay, we go, if we press on the slab, right click, we can go the most important thing that the loads 5.5 dead load and the minus z direction kilonewton per meter square, and for live load equal to. Okay, also right click, select and right click S30. We go to S30 here, define slab properties, S30 here, 30 megapascal, mat1 material. What is mat1? Okay, the mat1 material is here, F prime C equal 25 megapascal. Okay, gamma 25, modulus of elasticity equal to 23,500. Okay, so we check the material, the section, okay, the loads applied, and also we can show the load pattern. Okay, here, yes, for the self weight we can also the load combination. Here we have them, okay, exported from ETABS. Now if we can show the model is ready to go to run. Okay, we will run the model and we will show what we have. We need to save it as slab 11 meter. Okay, now the SAFE do the run. We will wait until the SAFE terminate. If we remember, when we do run an ETABS, also this is the short term deflection. Okay, it's the same deflection that the ETABS give us, minus 15 approximate 1.5 centimeter. Surely this is here, this deflection, maximum deflection, but this deflection is a short-term deflection, sorry, only on from dead load. So it we cannot do our own analysis only for this deflection. We want to check also the long-term deflection. Before this, we want before checking the deflection, we want to check the punching shear. Okay, because this is a flat slab. So all the numbers below 1, the punching shear is safe. We can show here the punching for this column. We have 4.7. So the punching shear at this column is very, very dangerous. Here 1.3, 3.5, 4, 1 point. Okay. So for these columns, we must increase the area of the slab here, okay, because corner column like this is dangerous, it's not safe. Okay, here also, so we have problem for this columns, this columns, and this columns. We will check this. So now we will check also, we need to increase the area here around these columns, and we need also the increase the area here Okay, also we need to increase the thickness. Here for these columns the area is sufficient, but the thickness of the slab not sufficient. Okay, and the standard way or and the main the main the thickness is the main reason affecting punching shear. But here for this column and this columns, the problem is with the area around the columns here, because there are corner columns. Okay, so when we need to make the slab efficient against punching shear, we need to increase the thickness slab. But for these two columns, we need to also increase the thickness of the slab and increase the area. Let's show also before and look the run. We need to show the deformed shape. But before go to deformed shape, we need to define the long-term deflection. How we can define the long-term deflection? We can define the long-term deflection for this slab by do a combination. Combination of what? We will show now. We go to define. So now we need to define long-term deflection for this slab. How we can do this? We go to define load cases, add a new load cases. Okay, we can name it at D1 non-cracked, and here we put one dead load and one live load. We press OK, and now we do add copy of this. We name it at D2. Sorry, D2. Here we put nonlinear long-term cracked. For the creep of the concrete, the maximum number coefficient is 2. So we put it because the slab we need to put the long-term coefficient with maximum coefficient of long-term deflection. Okay. The shrinkage strain also, the maximum number is 5, 0.305. So we put this coefficient, the maximum. Okay. Now we put here one dead load with 0.25 live load. Okay, so with long-term deflection we put only 25% of live load. Also we need to add one with nonlinear and here with 0.25. Okay, then we go to define load combination, add a new, we name it long-term deflection. We put D1 with D2 minus 1 D3 and we press OK. Okay, now we can do run. We didn't do any change with the thickness or area of the slab. We need to show what this slab of 30 centimeter give us long-term deflection. Okay. So we do run of SAFE. When we do run with long-term deflection, the time of running do take more time. Okay, the run step take more time. So we have the same short deflection because we didn't change anything with the parameters of the slab. Now we can go to display. We need to show the long-term deflection, but before showing the long-term deflection, we need to know the limit of the deflection permitted on this and this slab. We have the maximum, okay, the maximum span here is equal to the 11 meters, so equal to 11,000 millimeter divided by, and the normal way we put 240. Okay, but here we have glasses walls. So for glasses wall, the ACI code say that when we have glass walls, this number equal to 480. Okay, so uh, we need to divide this number or multiply this number by 2. So the limit divided by 2. So we have 23 millimeter or 2.3 centimeter limit permitted for deflection. Okay, so let's show what we have. If we go to load combination, show deformed shape, we go to long-term deflection and we apply, we can show minus 79 millimeter. This is a very large number, approximate minus 79, and the limit is 23. So the slab is unsafe. So let's go and we need to increase. Also here we must check that the stuff equal the same thickness of the slab. The stuff is the part of rigid area for the beam, the walls, the columns, the rigid area around the beam, the columns and the walls. So connected with the slab. So this number of this area, rigid area, must be the same thickness of the slab. Okay. So anyway, the stuff must be the mass thickness with the for the slab. Okay. So let's increase this thickness to 7 centimeter. So the thickness of the slab will be 37. Okay. Can change the name to remember the thickness. Now let's go and do run. So we increase the thickness of the slab 7 centimeter and we will show. First of all, we need to check the punching shears and the long-term deflection. So now we wait until the software, the SAFE, terminate from analysis and calculate the result. And we remember we take on into consideration the maximum number of creep and the shrinkage for long-term deflection. So this is the best way and more safety way to get a very safety slab. So we are wait until the calculation terminate to check the result. And also we need to know that first of all we need to check the punching shear, and especially for this columns and this columns, and we say that the problem of these two columns also is the area. Okay, first of all we remark or we note that the short-term deflection decrease 5 millimeter. So we instead of minus 15 we have minus 10. Okay, now we need to check the punching shear. For these columns, the punching shear is safe now, but we have stay problem with these columns and with this column. Okay, so we need to increase the area here to help us to make these two columns safe under with punching shear. Okay, all the other columns is safe. Here also we have problem. Okay, let's go to show the long-term deflection. We go to display. Okay, deformed shape, load combination, long-term deflection, apply. We have minus 51. Okay, so still have big problem also. Okay, with this deflection. So we can unlock the calculation. First of all, we need to increase the area around these columns. So we select this edge and this edge and we go to edit area. Let's increase for 1 meter. Okay, sorry, here the millimeter. So 1 meter equal 1000 and for this here also, and this way edit. Okay, and this, yes. Okay, and here why may, but because we have an arc. Okay, anyway, let's try. Now we need to check the punching shear. We need to wait again. This is a very important thing, especially for foot slab. Beginning the checking the we must begin to check the punching shear. It's very 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 critical thing. Okay, and we began to check the punching shears and long-term deflection. Then we do the analysis of flexural moment, bending moment, and we put the reinforcement, required reinforcement. So we increase the area around this two columns. Okay, and we need to check the punching shear. So the same short term. Now we need only to check the punching shear. Here 1.16 and 1.23. We can show that when we increase the area, we have good effect. Okay, effect. So now we unlock the calculation. We can go. We need to increase more the thickness of the slab because we have unsafety against long-term deflection, and we have some columns are not safe against punching shear. Let's go and put the thickness of the slab, sorry, here 42. Okay, and here we put 42 and we press OK and OK. Let's do run. Now we increase also the slab for 5 centimeter. And we will show what we will have. So we increase 5 centimeter, and surely the punching shear is safe for this columns and this columns and this columns, because we increase the area and we increase the thickness now. Okay, we will check also now the long-term deflection. So we have a very large thickness. So if now the long-term deflection, okay, is not safe, we need to go to other method of other solution from increasing the thickness of the slab, because we cannot increase more the slab. 42 centimeter is very large thickness. Okay, so we need to think about other solution for this, for long-term deflection. Let's now wait under the calculation terminate, and we will show what we'll have with the punching shear and long-term deflection. And we must didn't forget that we didn't need to use post tension. Okay, for many reasons the owner didn't need to for the cost and for the fabrication or difficult construction and the site. Okay, because the calculation terminate, we have In the short term, we note that decreased to -8 millimeter. Let's check first of all the punching shear. So we have now all the slab is safe against punching shear. Okay, so now we are safe under punching shear. Let's go and show the deformed shape under the long-term reflection. So we have -38. The slab still ain't safe for long-term deflection. So now we must think about other solution. Okay, for this slab, we didn't need to increase more the thickness. Okay, so let's unlock the run and let's try to go to material and to use a concrete FRMC 35. The 35 have long E modulus of elasticity equal to 75,805. That's okay. And let's now show how much the FRMC affect the slab. Okay. So now we do the run. And we increase the FRMC of the slab. We forget to assign this FRMC to our slab. So we do calculation without so we make a mistake because we do the calculation without assigning this FRMC for our slab. So we must wait to terminate the calculation and then assign this material for our slab. Okay, so now we wait under the calculation terminate. And we need to unlock this calculation and go to define slab. Here first of all we need to go to here made to, okay, and check here for this slab. Okay, made to also. Okay, and let's go and recheck on the made to 25. Yes, okay. Now we can do the run and we will show how the FRMC, okay, affect the long-term deflection of this slab. So we can remark that the short-term deflection decreased to -6.95. So the FRMC, the increasing of FRMC decreased the long-term deflection. Also here we have, okay, the FRMC, the increasing of FRMC increase the work of the slab against punching shear. We need to check the long-term deflection. Okay, so also the increasing of FRMC give us a very good result, -29 also. Okay, so the limit is 23. We need to increase also or decrease this long-term deflection to -23 megapascal. Okay, so now the solution that we have, okay, also to put a beam from this point, from this columns to this wall, and the middle, okay, the middle area here, the most dangerous area here. So we can go to define beam, modify. First of all, let's put the material of this beam is the same material of the slab, FRMC equals 35 megapascal, because we need to cast beam with the slab. Okay, it's more efficient. Okay, we need rectangular beam. Okay, let's put the width of this beam equal to 40 centimeter, 400 millimeter, and the depth, minimum depth must be equal to 400 millimeter, because when we have, for example, a slab like this, okay, and we need to put a beam like this area here, okay, this area here must if we name it h1 must be equal minimum to h2. Okay, so the thickness of the slab equal 42, so the here the total length of this beam must equal to approximate 80 centimeter or 800 millimeter. Okay, so let's return to here, we put this, we press OK, and we can go to here, draw beam lines. Beam 1 can go from this point to this point like this. Okay, now we can go to do run, and we will show what we'll have. So we add a drop beam here. Okay, even as the drop beam pass above the opening, it's not a problem. Okay, because the problem, this opening is very large, so we can get or uh, pass through it a 40 centimeter. It's not a problem. Okay, and we will remind that this is a stair, so we didn't have any problem. And we will do also a thing here, we will show after this, because we assume this opening, this and this and this and this, the stair as open. We will show what we will do for them also. Because usually when we have opening, this opening affect the slab negatively. Okay, so when we have many opening of the the slab will be more weak. Okay, so let's go show first of all punching shear. Okay, the same number, so we can show now we have minus 24.4, so the limit is 23 minus 24, the difference is 1 millimeter. It's not a problem, so we can say now that our slab is very very safe now. Okay, and especially for long-term deflection and short-term deflection and punching shear design. Okay, so punching shear design, we can check it from this option, and here with the combination that we define them and load cases. Okay, we can check the long-term deflection from this, and the short-term deflection is get it directly after run. Okay, first of all, we increase the area to solve the punching shear problem with this column and this column. Okay, we increase the thickness for solve the punching shear columns in general. Okay, we increase the thickness of the slab to decrease the long-term deflection. We get 42 centimeter thickness. Then we increase the material FRMC. Okay, flexural strength of material. Also, we put a drop beam with thickness equal total thickness 80 centimeter from this column to this columns and the most dangerous area, so we get the best long-term deflection. Okay, with maximum coefficient of long-term deflection for creep, cracked and shrinkage. Okay, so it's very very now safe slab. Now we need to design the fractional, we need to show let's So we unlock the run and we do run again because we have an error. So now we can go show slab design. We need to design the reinforcement of the slab. Okay, so we must go to here. Design basis, the method of design finite element. We need to impose the minimum reinforcing. So the area which have minimum reinforcing, we need to put the minimum reinforcing. Okay, because if we didn't check this option, we may have reinforcement below the minimum. So we need to, it's very important to check this, use this option. Also, I need to say something. We can, for example, for this part of slab, this part, to use a thickness, we can decrease the thickness of the slab to 35, okay, to 37, okay. It's not necessary to make all the thickness of the slab, okay, but for safety, it made the owner for after time delete these columns from the plane. And here the same thing, we need to calculate also the effect of this option. It may an option for the owner. So if we can make all the slab 42, it's good. Okay, so now let's continue to do the reinforcement of the slab. We choose this option, typical reinforcement. Okay, we begin with the top direction 1. So the top is this top rebar, and this direction 1 is the X direction. Let's use 16 or 14 at the beginning, each 15 millimeter, sorry, 50 centimeters, so 150 millimeter. We'll show it's a good reinforcement in this direction. We have some direction it's not good here. Okay, it's point, so it can be safe. Okay, we need to when we have opening, we need to increase the reinforcement and around the opening. Okay, like this, inclined 45 degree. Okay, and X and Y direction, we must increase the reinforcement. For bottom reinforcement, also it's a good reinforcement option. Direction 2 also here, because the thickness of the slab is very large, so the reinforcement it's good. So we can use 40 millimeter bars and the 2 direction, but we have a very large reinforcement. In my opinion, we must use 16 rebars. Okay, because with large thickness, okay, it's necessary to use also for 42 centimeters 16 millimeter of rebar. Okay, so now we can put all the reinforcement equal 16 millimeter. So we press close. So this is the full design reinforcement deflection punching shear of this slab. This is the first design. We need to do many design and merit check also on this slab, but we will do in the next lecture. Thank you for your listening. We'll continue on the next lecture.